I'm Nicholas, and I'm going to talk about what happens when machine learning isn't designed explicitly to be private. So we're now using machine learning models on everything from our medical images to our text messages to our emails. And when we do this, the real question is what happens to privacy? So do these models leak sensitive information about our training data? And the reason why you can imagine that this wouldn't happen, the reason why you can imagine why maybe you get privacy, is what we have is like maybe all of you have training data, and you're going to contribute all your training data together, and we're going to use this to collaboratively train a big giant model. And now I'm going to be allowed to query this model. And so you can imagine that maybe it's hard for an adversary to do anything to be able to distinguish the case where we have all of this data and all this data plus one individual record. Like it's maybe tricky to distinguish these two cases, and so maybe there's privacy here just because of how much data there is. Now, there's a problem in that, at least theoretically, we've known for a long time that it's possible to have privacy violations. And we've known that academically, the theory people tell each other ghost stories at night about how it's possible that training data could be leaked in these machine learning models. The question is yeah, it's possible in theory, but are privacy attacks actually something that we can really do that matter in practice? Is this a real thing, or is it something that we just like to be worried about? And what I'm going to hope to convince you of in this talk is that the privacy attacks actually matter, and we can do them, and we can do quite strong attacks in practice. OK. And the way I'm going to do that is I'm going to first introduce to you what's called a training data extraction attack. This is an attack that we've been working on for some time. And it's going to be able to breach the privacy of individual people in a training data set. And the type of model I'm going to attack is what's going to be called a language model. And the way a language model works is fairly simple. It's just like any other classification model. And it takes some input text, and then it outputs a prediction of what it thinks the next word is going to be. So maybe the text is, hello, my name is, and it predicts the next word, if it was trained on my data, is Nicholas. And so then what you can do is the thing that makes language models nice is you can use them recursively. You can copy the output back to the input and then get the next sequence to go. And you can say what comes next, and it will say, this is Nicholas and. And then you can sort of run them this way forward, sort of recursively generating word after word until it gives you an entire sentence, maybe, hello, my name is Nicholas, and this is my talk. And it's not like they can do little small toy examples like this. The best language models can do really high quality text. So here's some example from the GPT-2 language model from OpenAI, where humans put in some text talking about unicorns. Humans said, in a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. And then the humans went on to describe one more sentence about these unicorns. And then we asked the machine learning model, OK, this is the prompt. Please complete what comes next. And it sort of goes word by word. The scientists named the population after their distinctive horn, Ovid's unicorn. And then it goes on from there to talk about various properties of these unicorns and how they were discovered and where they were discovered. And by all accounts, it's very, very nice text. This model is a very good language model and can write some high quality text. And the reason why these models are interesting is that not only can they tell us fun stories, they're also the kinds of models that we use when we train on our emails and our text messages. And so it's really important to understand if they're private. And so what I'm going to do is I'm going to show you an attack, which we call a training data extraction attack, which is allow us to violate the privacy of the training data here. OK. The way this attack is going to work is it's going to have two simple steps. The first step is just going to be to generate a lot of training data. A lot of data. Hopefully some of it will be training data. The reason why you expect that generating a lot of data should be easy is this is what models are designed to do. Like, the purpose of a language model is to spit out text. And so all we have to do is to ask it to give us a lot of text, and it will go and do that for us. And now it turns out some of this text is going to be training data. And the reason why is that when we train these models, the objective of training is to minimize the loss on training data, which explicitly encourages the model to memorize at least some of the data. The thing is, though, that there's a lot of text here, and it's really hard to filter the signal from the noise, the training data from the non-training data. And so when you just look at all of this, most of it looks fine, and so you can't actually pick out individual training sequences, even though some of them are there. And so that's where the second part of the attack comes in, which is what's called a membership inference attack, which you can think of as this magic black box that will highlight for you individual training examples from the data set. So we'll say, like, of all of the things that were generated, most of that is just benign text that it came up with by itself. But a couple of examples here are training examples. OK, so this question, how does this magic black box work? What it relies on is this property of machine learning models that they tend to have very high confidence on things that they were trained on. So let's imagine that I had two sequences. One of the sequences says my phone number is 0001234, and the model says the probability of this occurring is 1%. Probably this isn't training data because 1% is a fairly low probability. On the other hand, if I said my phone number is 5556789, and the probability of this occurring was 80%, this probably is training data because that's an abnormally high probability for something to have if it was not already in the data set. And again, like, this isn't something that just, like, I'm making up numbers here. Let me show you some actual data. What I'm going to do here is I'm going to train a bunch of models, either containing some example or not containing the example. In orange are the distribution of confidence values when you do train on an example. And in blue is the distribution of confidence values for different models when you don't train on an example. And so what you'll find is that when you train models, like I've trained 10,000 models here, lots of models. When you train models on an example, the confidence is like almost always big. And when you don't train on the example, the confidence is almost always small. And so it's really easy to separate, if you show me what the confidence value is, whether or not the model trained on this example or not. And as a result, I can very easily tell if something was training data, which allows me to do extraction, because I've generated this sequence already. OK. So let's go and actually evaluate this and see how well this attack works in practice. And the first thing we find, which is maybe a surprising observation, is that up to 5% of the output of language models is actually memorized training data. And this is a very big number. It's maybe surprisingly large. And it's so surprisingly large, actually, it turns out it's not entirely interesting to actually look at this number. A big reason why it's this big is because lots of repetitive text is sort of contained on the internet. And when you train models on repetitive text, it will spit out repetitive answers. So a lot of this 5% of data is just copying licenses of the MIT license, or copying various things that are repeated on the internet thousands of times. And so it's not all that interesting. So instead, let's not look at the absolute amount of data that's memorized. Instead, let's sort of look at individual examples of memorization. And for this, I'm going to look at memorization in the GPT-2 language model, which is the one that I showed you the unicorn text from earlier. This is a model that was trained by OpenAI. And we wanted to study this model because at the time we did the work, this was the best language model anyone had ever trained. And so we can be pretty sure that any privacy violations we find there are sort of general properties of machine learning and not accidental things that we find because we're attacking models we trained ourselves as privacy researchers. The other reason why this model is interesting is that it was trained exclusively on data from the public internet. And so that means that even if we could succeed in our attacks, the best that we're going to do is actually extract data that was already public. So we're not going to harm anyone here. OK. So what do we find? We find that we can get a fairly diverse amount of memorization out of this model. We get things like US and international news. We get lots of log files and error messages. We get licenses. We get URLs. We can find examples of personally identifiable information, contact information, these kinds of things. The thing I want you to take away from here is how diverse the amount of memorization is. And again, remember, this is not sensitive, but this is by design. GPT-2 was trained on data from the public internet, and so what you get is memorization that looks like things that appear from the public internet. But let's imagine that instead of training on the internet, you trained on some internal corporate data set. Then, instead of having memorization of US and international news, maybe you have memorization of internal company bulletins. And instead of memorization of log files of people asking for help on Stack Overflow, you get log files that contain user data. And instead of personally identifiable information that people put online by choice, you'll get personally identifiable information that was supposed to be private. And so this is the kind of memorization we're able to get out of these models. Now, let me tell you one experiment that hopefully gets at the question of why this happens. Why are we able to get this amount of memorization? And it turns out a big reason why is because models tend to memorize things if they're repeated more than once. And so what I'm going to show you here is what happens when we found a document that was contained in the GPT-2 training dataset that repeated various URLs between 8 times and 359 times. And then we can ask, for each of these URLs, we can go one by one and say, did our extraction attack find this one? Yes. Did our extraction attack find this one? Yes. Walk all the way down until we find that our extraction attack starts failing at things that are repeated 17 times or fewer. And so we can say, like, it looks like there's roughly a threshold here. The attack succeeds almost always when you have something inserted more than 17 times and never fewer. OK, so this is something a little interesting. Maybe you say, this is no longer a problem. If you repeat something 17 or 30 times, at this point, it's fine for the model to memorize it. I might disagree a little bit first, because I've probably told my family things 30 times that I wouldn't want made public. But even if I agreed with you, this 20 or 30 number is only one example. And it's only one example for one model. So what we can do is we can take a plot of like x-axis, how big the model is, number of parameters. This star is here corresponding to GPT-2. It's roughly 1 billion parameters. And on the y-axis, we have how many times you need to insert something before it gets memorized. And sort of I showed you one point, but I can expand this by looking at a bunch of different model families into a line. And what we find is that as you make models bigger, they memorize things that are repeated less and less often. Up until the point where maybe you reach 100 billion parameters, and models sort of look like they start, like, if the trend continues, memorizing things repeated just a handful of times. And maybe you say 100 billion, that's a big number. We're not going to train models that big. Sorry, but you're already wrong. The biggest models that exist as of last year are 1 trillion parameters. Like, we already have trillion parameter neural networks. And we're only getting bigger and bigger models as time goes on. And so this is really concerning, because it means that the machine learning community is pushing in the direction of bigger and bigger models. And as we've seen, bigger models means more memorization. And this is going to cause more of a problem as we go forwards. OK. So what are we going to do about this? Well, one thing you could do is you could try and add sort of privacy by coming up with some ad hoc defenses to prevent it. Let me tell you about just one example of what happens here. That's sort of an example from the vast space of attacks on ad hoc defenses. And the defense I'm going to tell you about very briefly is this paper that's called InstaHide, which got a bunch of attention and received some awards for being a very good defense to prevent exactly these kinds of reconstruction attacks. And this defense works not on text, but on images. And so what the way the defense works is you take a normal image, and you encode the image into some noisy version of this image. And then instead of training machine learning models on the original images, you only ever train machine learning models on these noisy images, and then use the models like this. Now, first of all, it's kind of weird that you can do this encoding and train models on noise and have them become good. That's kind of like surprising. I'm not going to talk so much about that. It turns out that you can do this. In their paper, they have some experiments that show tables like accuracy works. I don't really care about the accuracy. I want to ask the question, privacy. Like, if you were to do this and train models on these noisy images, why should you expect you to get privacy? And the argument in this paper is fairly nice, and it's fairly clean. The argument goes like this. If you train a model on only these encoded images, then if you could do an attack, you should never be able to recover the original image. The best you should be able to do is to recover the encoded version of the image. And because you can't go from an encoded image to an original image, you're fine. Like, you can use whatever machine learning you want. The best you'll be able to do is recover encoded images, and so just construct an encoding function that's one way, that you can go from an original image to an encoded image, but not backwards, and now you have privacy for free. And the question is, does doing this actually give you privacy? And the problem is that most of these encoding schemes don't actually have a proof of security. So if the authors write down that like they tried hard to break their encoding scheme and they couldn't, but that doesn't mean that you can't break it. And we actually show that in the case of InstaHide, it's relatively straightforward. And for some other encoding schemes, you can do them as well. And the general way that you do this is, like, if you squint really hard at the sort of noisy image, you'll kind of see that it still has some resemblance of the cat. And I could do some fairly simple local sort of convolution stuff to actually you can almost completely recover the image just from the noise itself. And if you work with pairs of images and do some fancy math and some graph theory, then you can basically completely recover the original images. The authors for these defenses put out challenges on GitHub asking people to try and break them. And what I'm showing on the top here are the original images that the authors included in their challenge. They, of course, included encoded versions of these images. And then we reverse engineered the original images from these encoded versions. And our reconstructions aren't perfect, but they're pretty close. They're about as close as you could get, hopefully, for images. OK. So this is not going to work to do some kind of ad hoc privacy, which brings me to the final point in this talk, which is what can we do if we can't rely on some kinds of ad hoc privacy proposal? And basically what we're going to do, what I'm going to propose is you can do one of four things. The first thing that we can do is just not use sensitive data. Right? If you only train your model on ImageNet data, then extraction attacks don't matter, because anyone who wants ImageNet already has a copy on their disk. And so it doesn't even matter if you have to do an extraction attack here. You can always just download the data. But let's suppose that we're in a setting where you can't rely on public data because the public data doesn't exist, and you have to rely on some sensitive data. Then you can try and at least just not release the models. If you treat machine learning models as private as the data that was used to train them, everything's fine. If everyone who has access to the machine learning model could have just gone to the data set, then again, an extraction attack doesn't matter, because the best thing that they could do would be to look at the data, but they already have permission to do this. Think, for example, if we had a data set which was medical images, and the only people who were allowed to query the model were doctors who had access to the medical images. This would be fine. Even if they could extract the images, they could just have looked at them directly. OK, but there are settings still where you want to release models to everyone, but have it be allowed that the people can query the model may not be allowed to access the data. Then what do you do? And one thing you can do here is apply what's called differential privacy. This is a defense technique which is provably correct. I unfortunately don't have enough time to tell you anything about how it works. But if you apply it correctly, then you're guaranteed that the reconstruction attacks that I've shown here cannot be done ever. It's not like no attacker will ever be able to do it. The math just sort of proves that you can't. There are some problems with differential privacy, though. It's a little bit slower. You lose a little bit of accuracy. Sometimes it's hard to define what sort of make the theory actually match the practice of definitions. But if you can set it up right, you'll be fine. But again, let's suppose that you can't. What if you can't use differential privacy for some reason? Then at the very least, what you should do is what we call an auditing, and audit the privacy of your models, and try and understand how private they are by attacking them and investigating their privacy in various ways. Again, this is something I can't go into very much now. Fortunately here, though, if you wait like 10 minutes, Reza is going to follow me, and he's going to give an entire talk on auditing machine learning models. And so you'll get all of the answers for that then. So with that, this is basically everything that I wanted to convince you of. The important takeaway here is that we understand that machine learning models aren't private by default, and that we can do attacks, and it's necessary to take some steps, maybe these, maybe others, in order to prevent these attacks from happening in practice. And so with that, thank you very much, and I'm happy to take any questions.